Okay, today's videos are going to cover periodic trends and periodic properties of elements. I'm starting with the original periodic table deduced by Mendeleev, and as we've already said, he didn't have the benefit of quantum mechanics to come up with this, but he still came up with an incredibly accurate periodic table that has many of the same relationships that we see on the periodic table today. He figured this all out simply by noting similarities in the chemical reactivities and the chemical behaviors of the elements. These are the periodic trends. Okay. In addition to looking at the elements that were known, he predicted, basically said, there ought to be an element here. There ought to be an element here. There ought to be an element here. Okay. He looked at where there were elements missing and said, those are going to be discovered one day. Rather than saying, no, I have to redo the structure of my table, he said, no, the structure of my table is right. There's just some elements that we haven't discovered yet. And you know what? Not only was he right that there were elements that remained to be discovered, he nailed their properties. So this is germanium. Germanium wasn't observed until 15 years after Mendeleev predicted its properties based on periodic the trends that he'd observed, and, well, you can judge for yourself how close he got. He nailed it. He absolutely nailed it. And so that's pretty astonishing, and it's a testament to how powerful periodic trends can be if you understand them and apply them correctly. Okay. Moving on. You've already done your group activity by this point. If you haven't, you need to make sure you complete that before continuing with this video. Okay, the group activity on periodic trends, you looked at atomic radii. We're also going to extend that to ionic radii in this video. But they're examples of properties that exhibit periodic trends for the elements. A couple of definitions. Atomic radius is defined as half the bond distance for a homonuclear diatomic. Okay, this example here is for chlorine, so the covalent radius of chlorine atom is 99 picometers, which is half the bond length of 198 picometers. A picometer is 10 to the negative 12th meters. That is, there are 10 to the 12th picometers in 1 meter. Okay, it's 1,000 times smaller than a nanometer. Ionic radius is defined slightly differently, and it is the radius of the element in an ionic compound. We can measure these very precisely, in some cases more precisely than the atomic radii, using a technique called X-ray diffraction. But in any case, we know what these radii are, and we're going to study the periodic trends in them. So, atomic size varies in predictable ways as we move across a period or down a group on the periodic table. This is what you explored in your group activity. One of the things. You also looked at ionization energy, which is the subject of the next video. Down a group, atomic radii become larger. Why is this? It's worth pausing the video and making sure that you can come up with this answer on your own, because it should really be obvious to you by now. The n quantum number is increasing. Remember, the n quantum number indexes the size of the orbitals that are being filled. The previous electrons have filled up the space closer to the nucleus, so the valence electrons have to occupy orbitals with higher n quantum numbers. Across a period, the atomic radii become smaller. Why is that? In your periodic trends group activity, you explored certain explanations for this involving Coulombic charge and number of valence electrons. We are going to do it slightly differently. We are going to introduce a new concept called effective nuclear charge, which actually explains not only the trends in atomic radii, but all the other periodic trends that we can think about on the periodic table. And we're going to talk about some of them, and then you'll learn about more in future chemistry courses if you end up taking them. In order to understand effective nuclear charge, we need to introduce the concept of screening. The idea here is that core electrons, as we've already discussed, are bound more tightly to the nucleus, so tightly that they don't participate in the chemistry of the elements at all. Only the valence electrons do. So another way of thinking about this is that the core electrons screen part of the nuclear charge from the valence electrons, and that's what's shown on this diagram over here. You see the nucleus, and let's say this is magnesium. That means the nucleus would have 12 protons in it. The core of magnesium is going to be neon, right? The nearest noble gas is neon, which has 10 electrons. The idea is that those core electrons each screen one proton from the nucleus, so that a nucleus that really has 12 protons in it looks like it only has 2 protons in it, because 10 of them are screened by the 10 core electrons in the neon noble gas core. So the 2 valence electrons in magnesium only feel an effective nuclear charge of 2 from the nucleus. We can actually write that down as a very simple equation, that the effective nuclear charge ZF is equal to the atomic number Z minus S, where S is the number of core electrons. In the magnesium example, Z was 12 and S was 10, and so we ended up with an effective nuclear charge of 2. Okay, so let's think about how this works. How does the effective nuclear charge, which is going to be sort of our primary periodic trend from which all the other ones can be deduced, how does the effective nuclear charge vary going from left to right across a row of the periodic table? Pause the video and think about that one. Okay, the effective nuclear charge going from left to right across a row is going to go up. Clearly, it has to, because it's talking about atoms with the same noble gas core, but with more valence electrons. So basically that, and therefore more protons. So this number, the effective nuclear charge, is increasing. And so what that means is that each valence electron is more tightly bound to the nucleus, and hence they're pulled in closer. So as you saw in your periodic trends group activity, the atomic radius decreases. Those valence electrons get pulled in and held more tightly, and so you get a smaller atom than when you have a lower effective nuclear charge. Okay, so we can extend this further and talk about the effective nuclear charge going down a group. Well, so pause the video and think about that for a second. Well, we've actually already covered this, right? The effective nuclear charge has the same value going down a group. Right? It has to, because you've got the same number of valence electrons, which means you're at the same point past whatever your noble gas core is. And since that's literally what you're talking about, that is going to be your effective nuclear charge. So why do we still see periodic trends? You should know the answer for that. It's because the atoms are still increasing in size down a group, as we've already discussed, because the n quantum number is getting bigger. But why does this matter? Why would this change the periodic trends, other than size, which is kind of inevitable? And this is sort of the next connection you need to make to really be able to use the effective nuclear charge idea to predict periodic trends. See if you can figure it out on your own. The valence electrons are further away from the nucleus when an atom is bigger. That means they feel less electrostatic attraction, even though the effective nuclear charge hasn't changed. So if you go from magnesium to calcium, which is going down one row in the same column of the periodic table, you've got the same number of valence electrons, you've got this 2, you've got the same effective nuclear charge, 2, but those 2 valence electrons actually feel a less of an attraction to the nucleus because they're further away. Okay, so let's follow this through. The periodic trends for the atomic radii are as follows. You've got down the group, they're increasing, and across a period, they're decreasing. You can see very clearly here, this gives you all the gory details in pretty colors. You can study it to your heart's content if you want to pause the video, but it's mostly just here so that you can really see and appreciate that the trends here are very regular for the atomic radii. Briefly, we're going to talk about ionic radii as we add or remove electrons from neutral atoms, the radii has to change, right? When you remove an electron and keep the number of protons the same, what are you doing to the effective nuclear charge? Well, basically you're increasing it, because although the valence electrons don't screen anywhere near as much as the core electrons, they screen a little bit. So if you have an effective nuclear charge of 2 that's only binding one one electron, that's going to be pulled in tighter and the radius is going to decrease. So removing electrons to make a cation decreases the radius. Adding electrons to make an anion is going to increase the radius, because now you don't have enough protons and enough effective nuclear charge to hold the electrons as close as when you have a neutral atom. So the next point is a key point. The ionic radius decreases across an isoelectronic series. That's just a big word that says you can write a series of ions, as we're about to do, that all have exactly the same electron configuration corresponding to a particular noble gas. Okay? So if we consider the noble gas neon, we can consider the ionic trend and ionic radii of a series of ions that all have that configuration. That 2 is supposed to be up. That's O2 minus. It's not peroxide ion. So that's supposed to be O2 minus, oxide ion, fluoride ion, sodium ion, and magnesium 2 plus. So the idea here is that the charge is going from 2 minus to 1 minus to 1 plus to 2 plus. And all of these things have the same number of electrons, but the nuclear charge that's holding on to them increases. So of course the ionic radius is going to go down. One important thing to realize here is you notice that we don't stick neon in the middle here, even though it sort of fits, right? It should go between the -1 and the +1. That's because atomic and ionic radii can't be directly compared, since they're measured by different means. Anyways, here's the periodic trends for ionic radii in another pretty picture, and basically you can see that the general trends that you would expect for the ionic and atomic radii are followed. Here are the trends for the atomic radii. They go straight across, but for the ionic radii, they don't key across a row, but rather they pivot around the noble gas table that's here. Here's that oxide, fluoride, sodium, magnesium progression. And you can actually include aluminum in there as well, the 3 plus in that series. If we then go to the next noble gas, which is argon, you've got sulfur and chloride, which have fewer protons than argon and so have larger ionic radii. And then you go to potassium and calcium, which have more protons than argon and so have smaller ionic radii. So you see that same trend in the ionic radii. And this is preserved throughout the rest of the periodic table as well. All right. That is the end of this video. You should go and answer the questions, the discussion questions now.